All right, let's do some approximations. Let's actually do something. So let's jump into it. So I have our linear approximations already written. These are linear, and this is a quadratic, aka a parabola approximation. So I have them written down. There's going to be a general formula, but what we want to do is we want to consider some function, and we'll make that function the natural log of x. Okay, so it's just the natural log of x, and we want to find a linear approximation to ln of x when we're at x equals 1. Then we're going to use the quadratic to approximate ln of x at x equals 1. And then we're going to use those approximations to estimate what's 1.05, a number that's near 1. It's not 1, but it's near 1. So we can see how good of an approximation can we have. So what we're really trying to do is we're trying to approximate what's ln of 1.05. That's our game. And if you were to punch this into a calculator, that's why I wrote calculator needed, 0.04879. ... It keeps going. So we're trying to approximate that number, trying to see by using a linear approximation and then using a quadratic. So let's just focus on the linear. So I'm going to steal this, bring it down. Hopefully don't take the prime. Yay. So this is what we're trying to approximate. So we're going to need to plug stuff in. So we're going to say P sub 1, and I'm just going to write it of x, is equal to f prime, or f of a. Well, f is ln of x. Our a is 1. I know it says x is equal to 1. So when we pop this in, we're like, well, it's ln of 1. There's your f of a. F of 1 is equal to the natural log of 1. Okay. Plus, now we need to plug in, now we have to put in our derivative. Now we're going to need to put in our derivative. Ooh. But, how are we going to do this? How are we going to do this? Well, we're going to leave these things as x's. So I'm going to jump aside and go, well, wait a second. If f of x is equal to ln of x, we now need to know what's the derivative. And I'm going to leave it all in terms of x's so then we can plug in at the end. What's f prime of the natural log of x? It's 1 over x, so we will replace it with 1 over x. Now we have x minus our a value. What's our a value? Our a value is 1. And there is a linear approximation. But we can do more work here. We can do more. Now, I wrote it in wrong. I wrote in f prime of x. Shoot. I need f prime of a. What's a? Isn't that 1? So isn't this 1 over 1, which is equal to 1? Oh, I'm so sorry. I'm so sorry. I should have wrote in just 1 times x minus 1. So we can say that the first degree, or our linear approximation, is ln of 1, which is 0, plus x minus 1. So a good polynomial would be x minus, or a line would be x minus 1. You're like, what? How is that a good approximation? What's going on here? Well, we have the natural log of x. We all know what the natural log of x looks like, don't we? I'll leave that in black. Comes up like this, takes off, like a 0, 1. And then we're saying that the line x minus 1, has an x-intercept, that this would be a pretty decent approximation. So there it is. There's our p sub 1, which is x minus 1. And it gives us a pretty good approximation because, well, it hits right at the same spot, right? That is the slope of the tangent line to the natural log of x. Well, that's the equation of the tangent line at the value of x equals 1. Now we're going to do a quadratic. We're going to move in. We're going to take another step here. So let's do this one. I'm going to try and be a little bit better this time. Let's try and be a little better. Let's explain this thing out more. All right. So we're going to want to use this formula, and we've got to remember ln of x is our function. And we're doing it at a is equal to 1. So let's do our work over on the other side. See, we need f of a, so we're like, all right, f of a is just f of 1, which is equal to the natural log of 1, which is equal to 0. now I move to this part. And it's like, well, we're going to need to find its derivative. So let's find the derivative on x, and then we plug in the number. If you can't plug in the number, take the derivative, the answer will be 0 every time. The derivative of the natural log of x is 1 over x, as we've seen. So then f prime of 1 is equal to 1 over 1, which is equal to 1. Cool. Well, x is just x, a is just 1, and now it says we need to find a second derivative. So we're like, okay, well, we need a second derivative on x. The derivative on 1 over x is negative 1 over x squared. Now we plug in our f double prime of 1. That's our a. That's the a. And that's negative 1 over 1 squared, which is negative 1. Okay, let's see it. Let's plug everything in now. So the secondary polynomial is going to be our f of a comes first. Our f of 1, that's 0. Plus our f prime of a. You already know what this answer is. We've already done it. We've already done it. It's up here. It's up here. The first two terms are going to be the exact same thing. It's just x minus 1, but I'm just building it back from the beginning. Maybe you see it better. So now we're like, well, what's f prime of a? Well, that one's just 1. Times our x minus a. Our a is still 1. That's the same thing we got from before. So the only thing we're actually doing is adding on this last term. So now we're going to say plus, all right, our second derivative at a divided by 2. So that's negative 1 over 2 times our x minus a. Oh, I wrote it in wrong. There needs to be a square up there. Oh, jeez. Why didn't you say something? All right, first degree, second degree. I forgot to write my square. Were you screaming about it? Were you seeing it? So now we can say that our second degree polynomial is x minus 1 minus 1/2 x minus 1 all squared. That's some sort of parabola facing down. How do I know it's facing down? Because the thingy on the squared has a negative in front of it. So I know it's some sort of parabola facing down. And there it is. We now have a fun-filled parabola facing down. So with this parabola facing down, I'm going to draw it in, let's go purple. Let's go purple. It looks like this. This is our p sub 2 of x, where it's starting to model the black curve, right? What's in black goes like this. And then our purple line goes like this. It's a little bit better. And as we continue going, our approximations will be better and better and better. Okay, so we've now come up with a first degree or a linear approximation for ln of x at x equals 1. We've come up with a quadratic approximation to ln of x at x equals 1. And now we're going to use the approximations to estimate 1.05. And as before, we know that this is what ln of 1.05 is, just plugged on into a calculator. And now we want to check and see, well, what would we get if we plug in 1.05 into our 2? So let's look at p sub 1, our linear, and let's put in 1.05, which is equal to 1.05. That's our x value, minus 1. So we find out that at 1.05, we got 0.05. Dude, that's a pretty good freaking approximation. If we were rounding the two decimal places, it'd be the same gosh darn thing. That's a great approximation when we're near 1. It's not a very good approximation if you get far away from 1. But it's pretty good here. Now let's check out our second degree polynomial. Let's plug it into that one. P sub 2 of, we're going to do our 1.05 again. I just changed the color up to show some difference. I'm terrible with color coding. All right, so we get 1.05 minus 1 at the beginning, but we already knew that. We already knew that. Come on. And now we're adding in the rest, that negative 1/2 minus 1 all squared, and then we put in 1.05. Now, we're not going to do this by hand. We'll punch this into a calculator and look and be like, it's not even a squiggly, sorry. It's actually a straight equal sign. This is 0.04875. you looking at these freaking numbers? They're damn near the same thing. They are good out to 4 freaking decimal places. 4 decimal places. It's accurate. Only by doing this twice, we can get a great approximation near 1. Near 1. And that is our game. That's what we're going to continue on. And in our next video, we're going to give you a general formula so we can play this game past just a second degree polynomial. Past a third, past a fourth, past a fifth. It's called a Taylor polynomial. So old Taylor is going to show us what's up. And I'll see you in the next video.